Kristina.
Yeah, thank you. So before the break, we basically stopped here. So we have now the ADM action written in ADM variables. And now we need to do what we did in classical mechanics and basically perform the Legendre transformation. So now our configuration variables for GR are the ADM3 metric, the lapse function, and this shift vector. And as usual, for each of these configuration variables, we introduce a canonical momenta. We introduce canonical momenta, which I denote by PAB, capital P and capital PA. So now we just do as what we did in our simple example. We introduce the canonical momenta by taking the here functional derivative with respect to the velocities. And you can compute this for the ADM momenta, which has this form. It includes, again, the extrinsic curvature and the inverse ADM metric here and its determinant. And if you look at these ADM action, you will immediately see there are no velocities involved for n and NA. And therefore, we are in the same situation as we had in our mechanical example. The momentum of the lapse function vanishes, and similarly for the shift vector. So we have primary constraints. Which means we have, in this case, because it's a field theory, we have 4 primary constraints, C and CA here, in terms of the momenta of lapse and shift. But this is a constraint for each space-time point, so we have 3 + 1 times infinitely many in the field theory case. Now we know we have primary constraints, so we have to apply what I was just introducing in the first lecture, the Dirac formalism for constraint systems. And we do this here by performing the Legendre transformation for those variables where it's possible, which is the ADM metric. And then keep the remaining velocities of lapse and shift as Lagrange multipliers. And if we do this here, we can do this for the ADM action of GR, which has the Lagrange density of this form. And then we add, as we have just learned, Lagrange multipliers lambda and lambda A for the primary constraints to this action. And from this, we can then read off the primary Hamiltonian. Now, if we do this and use that the velocities contracted with its momenta is of this form, that we have a contraction between the two ADM momenta, we can write it in this form here, where we have the primary constraints, and then in addition to that, we have the lapse multiplied by some phase-space function, which depends only on the ADM metric and its momenta. And similarly for the shift, which is contracted with CA. And these two functions have the explicit form here. So CA contains the covariant derivative of the ADM momenta. And C is more complicated. It has some contraction of the ADM momenta here in terms of this combination of the ADM metric. And then it includes the 3 curvature, which we had in our action. Now, given this, we now apply what we have just done in this general formalism. So we need to consider the stability of the primary constraints. And in the case of general relativity, this means the primary constraints related to the momenta of lapse and shift. Here is the primary Hamiltonian, just a combination of primary constraints and these 2 terms involving C and CA. Now, the Poisson brackets that we have in this ADM formulation is a standard Poisson bracket between the ADM metric and its momenta. So we have the coupling constant here involved. We have a 3-dimensional delta function at x and y. And because this is a symmetric tensor, we have some symmetrized combination of Konica deltas here, which are related to the indices which we have in the Poisson bracket. Similarly, lapse and shift and their momenta satisfy standard canonical Poisson brackets. Now, given this, we can compute the stability of the primary constraints, and we can explicitly write this down. And what we realize is, if we consider this for the primary constraint related to lapse, if we look at the primary Hamiltonian. So the momentum of the lapse just speaks to the lapse here. And similarly, the momentum of the shift vector just speaks to this term. They occur linearly here. So we just get the coefficients here in a sense, so C and CA. And the stability condition means that the primary constraints are stable if we add additional constraints to the system. So we are in case 2, because CA and C are not necessarily vanish on the constrained hypersurface, so we have to add them as secondary constraints. Now one calls C the Hamiltonian constraint and CA the spatial diffeomorphism constraint, for the reason that if we go back to this picture where we sliced our space-time, then C is generating diffeomorphisms orthogonal to these hypersurfaces, whereas CA is generating diffeomorphisms within sigma. So that's where these names come from. Now we have 4 times infinitely many additional secondary constraints encoded in these functions here on phase space. Therefore, the next step, according to the algorithm, is to check their stability. Now you can imagine looking at the action and the form of the constraints. This is something which is quite tedious to compute, but you can do this. And one does this usually not with the constraints directly, but one considers smeared constraints. And by this I mean that we consider the Hamiltonian constraint integrated over the entire sigma manifold and then multiplied by the lapse function, which I call C of n. Similarly, for the diffeomorphism constraint, we smear it with the shift vector and then integrate over all sigma. And also for the primary constraints, we introduce a C lambda in this form and a C vector lambda for the primary associated to the shift vector. In this way, we absorb the integrals in the primary Hamiltonian and can write it as a sum of these 4 or 8 individual constraints. So now one can show that if we consider Poisson brackets among only the secondary constraints, they satisfy the so-called hypersurface deformation algebra. So if we take, for instance, the Poisson bracket of 2 spatial diffeomorphisms, here shown on the top, we get a spatial diffeomorphism on the right-hand side with some modified smearing function, which is related to the Lie derivative along the shift vector m here of n. And similarly, if you compute the Poisson bracket between C and a diffeomorphism, you get back C here, again, with a modified smearing function, which is the Lie derivative along m of n, of the lapse function. And finally, you can also compute the most complicated Poisson bracket in this set between 2 Hamiltonian constraints, and you get a diffeomorphism constraint here on the right-hand side, which has a more complicated argument here because it's not only depending on the lapse functions n on m, but also on the inverse ADM metric. So in this sense, we usually say this is a Poisson bracket which involves structure functions because the phase-based quantity is in particular QAB inverse enters in particular here. Now, why is this important? On the one hand, it's related to the geometrical interpretation the constraints have I was just mentioning. But on the other hand, if this algebra is given, it tells us also something about the stability of the second-class constraints. So let's go back to the primary Hamiltonian. If we now analyze the stability of Cn and C vector n, then we know they will trivially commute with the primary constraints because these are just momenta, and different momenta in phase space commute among each other. So the only contribution in the stability analysis comes from the Hamiltonian and diffeomorphism constraint. But this algebra tells us that any combination that will show up in the stability analysis can be written in terms of these constraints again on the right-hand side. And therefore, we know that they all weakly vanish, and there are no further constraints, and there are no Lagrange multipliers to fix. So this is, in a sense, case 1 for the stability of these secondary constraints. And this means the Dirac algorithm ends here, and we can write down our final set of constraints consisting of the 4 primary C and CA, and the 4 secondary curly C and curly CA, and the 4 secondary C and CA. This I will just denote as CI, where we have 8 times infinitely many constraints here, so I runs in this case from 1 to 8. Now we do the classification, and we see that all of these 8 constraints are first class because the momenta commute with each other and with any other thing, so they are even strongly vanishing. And due to this hypersurface deformation algebra, we also have the situation that any of the secondary constraints can be written as some combination of them if we allow structure functions here on the right-hand side. And this means all constraints which are occurring in the setup of Hamiltonian general relativity are first class. So now, given the primary Hamiltonian, we know the final set of constraints, and this basically defines the final constraint hypersurface. There's one special thing about general relativity, because if you look at the primary Hamiltonian, it's just a linear combination of constraints. So there's no H naught as in the classical mechanical example, which means if we go to the constraint hypersurface, which should describe the physical sector, our primary Hamiltonian is vanishing. And I will come back to this point later. This is the problem of time mentioning in general relativity, and it's related to the fact how we can describe dynamics of gauge invariant quantities of these Dirac observables, which I was introducing in the lecture before. Okay, now so far we worked in the extended ADM phase space, so where lapse and shift and their momenta are elementary variables of our phase space. But if we look at the equations of motion of lapse and shift, going back to the primary Hamiltonian, they will only speak to the momenta which are involved in these constraints here. And what we will obtain for the first derivative of lapse and shift are these Lagrange multipliers, yeah, which are for a first-class system arbitrary, so they are not fixed by your system. And therefore, in addition, if we look, if we want to compute the dynamics of the ADM metric and its momenta, it will only be determined by C and C vector, so there is no contribution from the primary constraints. And for this reason, one often goes to the so-called reduced ADM phase space, where you basically solve the primary constraints. So what I told you about the final set of constraints means that you can always decide to implement a subset of your constraints, and then you go to a so-called partially reduced constraint hypersurface. And one does this usually, so by taking these equations of motion here into account, we realize they are only determined by lambda and lambda A, as I just explained. And therefore, if we reduce with respect to the primary constraints, we can work with this reduced action where only QAB and PAB are our elementary phase space variables, and we can treat NA and N as Lagrange multipliers in this reduced phase space. So by fixing N and NA, we still determine the slicing that we want to consider, but the difference is that these are no longer phase space variables here, but really Lagrange multipliers. So they will trivially you can trivially pull them out of the Poisson bracket of PAB and QAB. Then the so-called canonical Hamiltonian does no longer include the primary constraints, but it's just written as a linear combination of the Hamiltonian and the diffeomorphism constraint. Now, given all this formalism, you might be familiar with the Einstein equations in the Lagrangian formulation, which I had on one of my first slides. So how can we rediscover that equation in the Hamiltonian formulation? We have first order equations for QA and B and PAB, which are just given by taking the Poisson bracket of those variables with respect to the canonical Hamiltonian here. And in addition, all these variables are not independent because we have to respect the constraints, which are in the reduced case, the Hamiltonian and diffeomorphism. Now this system here in the upper box is equivalent to the Einstein equations in the Lagrangian case. And since I restricted to vacuum, we really have just the zero here on the right-hand side. Now, if we want to extend everything I said to the case of matter, where we have something which is sourcing the geometry here on the right-hand side, this can be easily done. Just follow the same procedure. You have two actions, let's say Einstein-Hilbert and some meta action, or even several of those. And then you can perform the same analysis. You will end up with the same 8 constraints. So the same primary and the secondary constraints get modified in the way that you have the contribution of general relativity, which I call CGU here. But then depending on the matter, so I just introduced a scalar field here, but even if you have more or other matter, you will get additional contributions in the secondary constraints, which are caused by that you coupled matter. Nevertheless, they satisfy the same hypersurface deformation algebra, so the stability is also ensured if you add matter. Now let's just summarize a little bit by counting the number of degrees of freedom. So we started with Einstein-Hilbert in 4 dimensions. So we have a metric on a 4-dimensional manifold here. And this has, since it's a symmetric tensor, 10 degrees of freedom. Now in the ADM setup, these 10 degrees of freedom were encoded in the ADM3 metric, which has 6 degrees of freedom. And the remaining 4 are encoded in lapse and shift. We had 4 primary and 4 secondary constraints. All of them were first class. And each first class constraints reduces 2 degrees of freedom in phase space. So if we consider the phase space degrees of freedom we started with, these are 20, so 2 times 10. We have 8 times 2 constraints. They reduce 16 degrees of freedom. So we end up with 4 physical degrees of freedom in phase space if we consider vacuum GR. And then, of course, additional degrees of freedom if we couple matter. So if we restrict to vacuum GR, we get in configuration space, again, these 2 physical degrees of freedom that we also have in the Lagrangian setup. So the counting of degrees of freedom works, and this entire Dirac algorithm, in a sense, gives you a nice way to count the degrees of freedom you have in your system. Good. Before I move to the next subsection where we want to start to introduce Ashtekar-Bardéev variables, let me again ask you whether there are questions to the last part. I see one.
Yeah. So if we consider GR as a field theory in terms of the metric, and if we see from the Einstein-Hilbert action, it seems that it is actually second order actions in terms of the metric. So shouldn't we, when we start the canonical formulations, we also consider a higher degree of freedom corresponding to the derivative of the Lagrangian with respect to the second order metric in terms of the actions?
Yes, so that's a good question. If you consider this here in this formalism, it works out, although we have higher order derivatives. So if you go beyond general relativity, where you have modifications of GR, this problem occurs, and you have to take care of also in the phase-space formalism by basically introducing additional momenta which compensate these higher order derivatives of the metric. But here it still goes through.
But I still don't get it, because in the Einstein-Hilbert action, shouldn't we have also second order metric in the derivative?
Yes, but this doesn't contradict that you have these Hamiltonian equations in the end, which are first order. I can combine them. Yeah, as usual in quantum mechanics, if this was your question, you just combine, sorry, I have to go back. So if you combine these two equations, you get the Lagrangian second order equation. So that's the same as in classical mechanics. Yeah, you just take a second derivative here, which involves the derivative of the momentum. You plug it in as in classical mechanics, and you will get a second order equation for the configuration variable. So that's why I said it's equivalent. So that's even a question you could ask in classical mechanics. Yeah, for the harmonic oscillator, we would also have just these two equations, first order. But of course, you can combine them and get a second order equation for Q.
Okay, thank you.
Looks like that's all.
Okay, further questions? Okay, now we have these equations of motions for the ADM metric and its momenta, and as we said, we can combine them to a second order equation. And you could basically use that setup and try to apply a canonical quantization. And people have done this. You can write down a quantization in terms of ADM variables. The problem is a little bit that's rather a formal quantization. So when we aim at formulating a quantum theory, we would like to write down a corresponding Hilbert space, and we would like to write down operators which act on this Hilbert space, and then formulate the quantum Einstein equations in this way. And if we do that, it's more convenient to go to a different set of variables where this can be done along the lines of techniques that have also been applied in other quantum theories. And this was the motivation to go from these ADM variables to the Ashteka-Barbero variables. Yeah, so if you quantize in ADM variables, you get the so-called Wheeler-de Wit equation, which describes the dynamics in this setup. But it's in this sense problematic that the underlying Hilbert space is not rigorously known, and therefore the idea was to just change the set of classical variables and then obtain a quantum theory where you can really write down explicitly how it looks like. And the idea is to introduce so-called tetrads in GR. So let me first restrict to 4 dimensions. And then for a given manifold, we can at each point in the manifold construct its tangent space. Yeah, and if it's, in a sense, if our manifold is in addition equipped with a metric, we can also define what orthogonal means, or in this case, pseudo-orthogonal. And we can introduce a basis at each point for each tangent space, which I call E0 up to E3 here. And I just label this set of bases here with I running from 1 to 3. Now we can compute the metric in this basis, and it will have this form, which is basically eta ij, and ij are really these indices with which I label my basis. Now, this is known as so-called tetrads in 4 dimensions. We will later need this in 3 dimensions when we apply this to GR. Now, what does this mean geometrically? Suppose we have the tangent bundle here with fibers over M, and we take a point P here. Then we can consider a section here in the tangent bundle. And we can do the same for M cross R4. And then consider a basis of this section in M cross R4, which I denote by psi I, which is just a standard basis here in R4. And then we can understand these tetrads also as a map, which I call E, from M cross R4 to Tm, yeah, which takes a basis element psi I and maps it to EI, which we can expand in terms of a standard coordinate basis d mu here, where basically the components are denoted as A mu I. Now, if I choose these 2 bases, so for instance the coordinate basis d mu and the standard basis psi I, then is E is uniquely determined. And often one denotes the tetrads also by these components, by the map, or by the frame that I choose by choosing the basis EI. Now, given this map from M cross R4 to Tm, also the inverse exists, which maps from Tm to M cross R4. Here, I again are the internal indices, and by the inverse map, I can take an element of the coordinate basis d mu and map it to E mu, which can be written as E mu I Xi, so expanded in terms of Xi. And the inverse we would call the coframe, so the cotetrad. Now, if we evaluate the metric at EI and EJ, we can just do this by using this map E, and we see that this is equal to eta ij. And this means that our form metric G mu nu can be written in terms of the cotetrads here, E mu I, Ej nu, contracted with eta ij. And this means that we can express the degrees of freedom sitting in the four-dimensional metric also in terms of the cotetrads. And given this relation between the metric that we started with, formulated now in terms of cotetrad degrees of freedom, we can ask whether this relation is in a sense unique. And for this, we consider a Lorentz transformation, which transforms our tetrad here by a Lorentz transformation lambda ij. And now we compute the inverse metric, which is related to the tetrads and not the cotetrads, and express it in terms of this Lorentz transform tetrad. And we see if we do this, the Lorentz transformations enter exactly in a way that they cancel out, and the inverse metric expressed in terms of the transformed tetrad is the same as the inverse metric expressed in terms of the original EIs, which means that a set of tetrads determines a metric only up to Lorentz transformation, which means only up to SO13 transformations. And this is something which carries over now to the ADM formalism, where we want to apply this in 3 dimensions, where we want to express the ADM metric in terms of tetrads in 3 dimensions, which are triads, and want to do the same thing that is possible in 4 dimensions. And before I will do this, let me briefly explain the plan, how I would like to discuss this. So we start with the ADM phase space down here. We have seen these are our elementary variables. We have a diffeomorphism constraint and a Hamiltonian constraint. Now, by going to Ashtika variables, Ashtika-Barbero variables, we extend our phase space by additional degrees of freedom. And this is due to the fact that we introduce triads. Since we want to describe the same physics, we need additional constraints that reduce these additional degrees of freedom that we get by extending the phase space. And therefore, we will have also the Hamiltonian and diffeomorphism constraint, but we will get an additional so-called rotational constraint, which is exactly related to an SO3 freedom, which we have in 3 dimensions by formulating everything in terms of triads. Now, this is not the final form of Ashtika-Barbero variables, but we will perform 2 canonical transformations from that setup here to end up with the variables that we finally would like to work with. The number of degrees of freedom and also the physics is not changed by canonical transformation. The only thing is the explicit form of the constraints and also the explicit form of the rotational constraint. Now the question is, if we have these extended phase space and different variables, how can we rediscover the ADM phase space, which is describing our physics? And this we can do by reducing with respect to these additional constraints, here with respect to GJK, and here with respect to the GJ constraint. And one can show, and I will briefly explain why this is the case, that you then get back to the ADM phase space. which means you indeed describe the same physics even if you're up here and have chosen new variables. Okay, so the first step is, as we just discussed for tetrads, we rewrite our three-dimensional metric in terms of triads, which I denote as EAI and EJK here. In a similar way, we don't have the Minkowski metric here. This is just the Kronecker delta. And as before, the metric is written in terms of the co-triads, the inverse metric in terms of the triads. Now, we have this additional freedom, which was the Lorentz transformation in 4 dimensions. Here it's an SO3 transformation, so rotations. So it's only, the metric is only determined up to rotations of the tetrad. Now, if we look by introducing triads, we basically get 3 additional degrees of freedom, which are encoded in these triads, but not in the metric. And therefore, we will get this additional constraint. Now, here we have rotations, so SO3. But if we write this object here, and the E is written as EIA, it's expanded in terms of a Lie algebra element tau I, and then contracted with dxa, so it's an Lie algebra valued 1 form. Now, since the Lie algebras of SO3 and SU2 are isomorphic, we can also consider this as an Lie SU2 algebra valued 1 form. So why SU2? It's also more convenient later if you want to introduce, for instance, fermions. So we will stick from here on with Lie SU2 algebra valued 1 forms. Now, this object is a mixed tensor in the sense it has 1 internal degree of freedom and 1 spatial one. The spatial one is pulled with the ADM metric, and internal ones are pulled with Kronecker delta ij. Now, this is only 1 degree of freedom. Remember, in the ADM setup, the momenta were related to the extrinsic curvature. In these new variables, we want to introduce another independent 1 form, which I call KJA, shown here. It's independent from the triads, and it can be related to the original ADM extrinsic curvature in this way. So KAB can be written as KJA contracted with EKB. And then the internal indices are contracted with delta JK. Now we know the extrinsic curvature from the ADM formalism is symmetric, so we can split this definition on the right-hand side here in a symmetric and anti-symmetric part, where the round brackets just denote symmetrization and the square brackets anti-symmetrization. Now, since the left-hand side is symmetric, on the right-hand side, the anti-symmetric part needs to vanish, and this is just what we call the rotational constraint, which I call GAB here. So this has to vanish for all AB, but it's anti-symmetric in 3 dimensions, so this gives us 3 additional conditions. Now, to consider the canonical pair that we finally want to work with, we do not consider the triads directly, but one considers so-called densitized triads. So we just multiply the triad by the square root of the determinant of Q, which gives E the density weight 1. And then we can understand this here as a vector, a Lie algebra valued vector of density weight 1. Now the triads, as the co-triads, satisfy these relations here. If you contract over the internal indices, over the spatial indices, you get a Kronecker delta in terms of the internal ones, and similarly for the internal ones. Now, if we introduce the densitized triad, the co-triad has this form, and you have similar relations. Given these rotational constraints, if this vanishes weakly for all AB, we can contract this with the densitized triad here, EA and EB. And this is equivalent because if the left-hand side here vanishes, also the right-hand side needs to vanish. Here it's a condition on AB indices. We have carried this over to a condition on the internal indices, JK. Now, given this, we can express the right-hand side in terms of these independent one-form KAK, contracted with the densitized triad, and rewrite the rotational constraint in terms of the variables that we want to use, namely the densitized triad and the other independent one-form KAJ. Now, given this set of variables as elementary variables, so these KJA will become our configuration variables, and the densitized triad the momentum. They satisfy also standard Poisson brackets. The factor of kappa over 2, which occurs here now, is due to the fact that you get an additional factor of 2 if you rewrite the action in terms of these variables. Now the constraints, which were already there next to the rotational constraints, are the Hamiltonian and diffeomorphism constraint. And the only thing we need to do now is to express those in terms of our new set of variables, which is shown below here. And similar to the other set of variables, you can see that the Hamiltonian constraint is the more complicated form also in, or the more complicated constraint also in this new variables. So now we basically need to express the R3, which I wrote down here, also in terms of these new variables, which can be done, but of course the box is limited here. That's why I basically just wrote R3 here, but it's understood as a function of K and E, and one can write this down also explicitly. Now, given this new set of variables, let's go back to the picture I had at the beginning. We are now here on the top, and the question is, does this describe the same physics as the ADM formulation? And therefore, we would like to ask the question whether we can perform a so-called symplectic reduction, which means we want to implement the rotational constraint and see whether we get back to the M phase space. So how can one do this explicitly? We had as ADN variables the metric and its momentum. Now we can express those in terms of the new variables. Yeah, this is shown here in the box. You see that the densitized triad is describing the degrees of freedom of the ADM3 metric, so there's no extrinsic curvature here. So the geometry of the metric is now, as expected, encoded in the densitized triads. And the momentum includes a mixture of densitized triad and the new variable which we related to the extrinsic curvature. Now, given these functions, you can plug them into the Poisson brackets with respect to K and E and compute the result of the Poisson brackets between these elementary variables. Yeah, and if you do this, because as we just saw, the ADM metric only depends on the densitized triad. They commute among each other. So we get trivially that the Poisson bracket, including two ADM metrics computed with respect to the Ka variables, is 0. So this is already fine because we get the same result in ADM. Now one needs to compute the mixed bracket where you have non-trivial contributions, because this includes the extrinsic curvature-like variable here. Yeah, so you have non-vanishing contributions, but one can also show that this yields the standard Poisson bracket with the factor kappa here again. Now a bit more complicated, because PAB has both variables in that expression here, is to compute the Poisson bracket between two ADM momenta. But one can show that the result here can be written as a linear combination, or like terms which involve at least linearly the rotational constraint. Now, if we go on the constraint hypersurface of the rotational constraint, all these terms involving G will vanish, because these G with upper index are a combination of the GJKs. And therefore, if we implement the rotational constraint, also this Poisson bracket will vanish, and we can show that both formalisms yield the same result and therefore also describe the same physics. Now, given this, we can write the action in this form. Yeah, here's the additional factor of 2 I was mentioning before. And take this as our starting point. The constraints will be the same, Hamilton diffeomorphism, and then this additional rotational constraint. Now, I mentioned before that for the stability of the constraints, the algebra of the constraints is quite important. And since we now have an additional constraint, we have to check how the algebra needs to be extended. And for this purpose, we also smear this rotational constraint in this form here. So we consider Lagrange multipliers lambda jk here, which contracts the internal indices, and then integrate over the entire sigma. Now, given that we had this hypersurface deformation algebra involving the Hamiltonian and the diffeomorphism constraint, one can show that this algebra is still valid, but we get additional constraints, additional contributions on the right-hand side, which are linearly in these rotational constraints. So on the full constraint hypersurface, it's still the same, that they weakly vanish. Also, we have to consider the rotational constraint algebra. And we see if we take 2 rotational constraints, we get another rotational constraint with a different smearing function here, depending on lambda 1 and lambda 2. And this is also what we would expect for SO3 rotations. Which means that if we perform the symplectic reduction at the level of the algebra, we also agree with what we get in the ADM case. And moreover, this kind of relation also tells us that these new constraints are stable. So now I have how many minutes left? 14. Okay. So then let me maybe start, because now we have this new set of variables k and e. We have shown that's equivalent to the ADM case. And now we want to go to Ashteca-Barbero variables. And as I said on this picture, this will mean we perform 2 additional canonical transformations, to go from the left box to the right box. And in order to describe these canonical transformations, we need the notion of the spin connection, which becomes relevant here. And this will also allow us to take covariant derivative in terms of tensors which have mixed indices, so indices which include internal and spatial indices. So let me consider maybe the case where we have a tensor which has entirely internal indices in 4 dimensions. We could transform a tensor of spatial indices in terms of tetrads into a tensor which has only internal indices. And using the inverse map, we can also do this from a tensor with space-time indices to a tensor of internal indices. And again, we have this relation between the 2 bases we just had before, and we can, in a sense, choose whether we expand some vector in terms of psi or the coordinate basis. Now, if we consider a covariant derivative acting on our coordinate basis, we get connection coefficients, which I called gamma here. These are for GR, the usual Christoffel symbols. So if we apply G mu, D nu, we get a linear combinations of D rho, and this linear combination is exactly described by the Christoffel symbols. Now, if we apply a covariant derivative on an object with internal indices, we also get connection coefficients, but in this case, these are the spin connection coefficients, which have 1 space-time index and 2 internal indices. Now, if you apply a covariant derivative on an object with internal indices, you see there is the standard spatial derivative contribution. Then there is a contribution for the upper and lower internal index. And if we have a mixed tensor which has space-time and internal indices, you get basically both contributions, one from the Christoffel and one from the spin connection. Now, using that, I can in principle decide whether I express the covariant derivative of V in terms of the coordinate basis or in terms of the tetrad basis, I can basically obtain a relation between the Christoffels and the spin connection, which shows up here in the second case. And if I do this, I can solve for the spin connection and express it in terms of the Christoffel symbols and the tetrads here and its derivatives. So either I use this argument, or we know that for the Christoffel symbols in GR, we require metric compatibility and torsion freeness. And if we carry over the metric compatibility to the tetrads, then you have a relation like this, which also allows you to give the same relation between the spin connection and the Christoffel symbols. Now, doing this and considering the covariant derivative of the metric evaluated in the cotetrad basis here, we get a condition due to the vanishing of the partial derivative on eta ij here, which relates the indices, the internal indices of the spin connection. Yeah, so we know since this needs to vanish, the internal indices must be antisymmetric if I swap them. So understood as a matrix, omega mu ij is an antisymmetric matrix. Now if we go again back to 3 dimensions, I denote the corresponding spin connection by gamma. It has now not a space-time, but a spatial index A, and it has the internal indices lowercase I and lowercase g here. From the relation we had here in 4 dimensions, we can carry this over to the 3-dimensional case and get a relation of the spin connection in terms of Christoffels and triads and its derivatives. Similarly, for the 3-dimensional case, it's also, of course, antisymmetric here in the internal indices, and therefore we can also understand gamma Aij as an antisymmetric matrix. Now, in order to write down the final form in which I need the spin connection, we use that we can relate an antisymmetric matrix in 3 dimensions, which has 3 independent degrees of freedom here, to a vector, which I called UK, by applying an epsilon tensor here in 3 dimensions to the matrix and contract it. So this factor of -1/2 is necessary because if you apply this twice, you want the identity, and since 2 epsilon tensors contract to 2 deltas, that's where this factor of -1/2 comes from. Which means instead of working with gamma Aij, we can also work with gamma Ai, which is this combination of gamma Ajk, and consider this as the degrees of freedom sitting in the spin connection. Now, from this relation here, this can be carried over to a relation of gamma Ij in terms of triads, cotriads, and its derivatives, and it includes this additional epsilon factor here to go from here via there to that final equation. Now we want to express, here it was still in terms of triads and cotriads. We want to express this in terms of the elementary variables, so in terms of the densitized ones. You can just use the definition of the densitized triads in terms of the triads, and similarly for the cotriads. And you see you get the spin connection as a functions of the densitized triads and its derivatives. You can write this down explicitly, and this is quite a complicated expression, but nevertheless given here above. Now the 2 canonical transformations that we want to perform are the following. First, I would like to use these k and e variables, and I just want to rescale them by some complex number, which I call beta, and which is known as the Hermesi parameter in loop quantum gravity. Now, if I just rescale the configuration variable by beta and the momenta by 1/beta, this is a trivial canonical transformation. Beta can be pulled out of the Poisson brackets, so all Poisson brackets remain the same. The second transformation that I would like to perform is an affine transformation, which modifies the variable kja here, which is a D-algebra valued one form. And I add the spin connection that we introduced before to it, such that I get a new connection, which is the so-called Azteca-Barbero connection. And since K depends on beta, of course, also the Azteca-Barbero connection depends on beta, which means that I get a family of canonical transformation parameterized by this beta. So now one can ask the question, why didn't I put a beta here? But it turns out that if I plug in the rescaled densitized triad in the spin connection, it's basically the same as if I do not rescale the E, so it's invariant under this rescaling, and that's why the beta only occurs here at the K variable. So now, giving this new set, the first canonical transformation was trivial, but we still have to check whether this new Azteca-Barbero connection and the densitized triad satisfy standard Poisson brackets in order to ensure that this is indeed a canonical transformation. So one can do this for the densitized triads. Nothing has changed, so this is given because the beta is basically just pulled out. For this Poisson bracket between A and E, it's also not so complicated because you see what you add to K is just depending on E, so it will trivially commute with the E in the second entry of the Poisson bracket. Now the non-trivial computation is to consider the Poisson bracket of two Azteca-Barbero connections, because as you see, you have the spin connection in both entries, and you have the K variable in both entries, which give non-trivial contributions. So it's a long and tedious computation, but you can finally show that the Poisson bracket is also vanishing. So this means it's indeed a canonical transformation, and we can use this as our new set of variables. So now let's look at the constraints, and in particular at the rotational constraint. We would like to rewrite this in a way such that it has the form of a standard SU2 Gauss constraint. And this is exactly possible because we introduced this new Azteca-Barbero connection. So we already discussed that metric compatibility in terms of triads means that the covariant derivative, so the contracted with the triad here vanishes for all j. We can carry this over to the densitized triad, then it has this form. So now consider this expression here and write it in terms of the partial derivative and the spin connection. So in principle, there would also be a Christoffel because there's a spatial index, but since this is a vector density of weight 1, this exactly cancels out. So we can write this explicitly here in terms of the epsilon tensor. And now we want to use this in order to rewrite our rotational constraints in this form. Yeah, so it will depend on beta now in these new variables. We basically consider the combination which we had before, which we can write as an epsilon tensor contracted with the beta variables k and e. And we are free to add an additional 0 here, which makes our life nicer. And this 0 here comes from the 0 of the metric compatibility condition. Now if I do this, I can add the covariant derivative here contracted with the densitized triad. And since this will have a contribution from the spin connection from the top here, we can combine this and write it as the partial derivative, and then the epsilon tensor contracted with the combination of k, which comes from the rotational constraint, and the spin connection. And we see the combination that enters here is exactly the Azteca-Barbero connection, contracted then with the densitized triad. So I can introduce a new covariant derivative, curly d here, which includes the Azteca-Barbero connection, and which means that this rotational constraint can be written as a standard SU2 Gauss law here, by meaning that this Kerr-D derivative contracted with EA for all j needs to vanish, and these are again 3 additional conditions. So finally, let me just finish this lecture here. We also need to rewrite the remaining constraints in terms of these new variables. We will come back to this form also in the other lectures, but you see that the diffeomorphism constraint can be written as a term which includes the curvature related to the connection, which I call FJAB. So its explicit form is shown here. And there's an additional rotational constraint here. And similarly, the Hamiltonian constraint in terms of these new variables has this form, which also, as you can see here, is some expression, but then there are additional contributions from the rotational constraint occurring, which is also the effect why the algebra includes these additional contributions. Now, this Hamiltonian constraint was still written in terms of the kj variables here, but this is understood as a function of E and A by using this relation. Now, given this and the fact that my time is up, I will finish here, and then in the next lecture, we will take this as a classical starting point for our quantization. And the only thing which I didn't manage to display here now is that you can rewrite the action in this form, and you see it's again the standard symplectic potential here of A and E, and then you have the linear combination of the constraints. Now here the SU2 Gauss constraint, Hamiltonian and diffeom. And finally, you could ask the question what beta to choose. And as you can see, if we go back to the Hamiltonian constraint, if we choose beta to be plus minus I, the second term drops, which means the Hamiltonian constraint really simplifies, so this could be a convenient choice. However, if you look at this relation here, if the beta is linearly here in K chosen to be complex, it means that the Azteca-Barbero variable connection is a complex connection, which you can use, but then you have to add additional reality conditions to your theory to ensure that the final variables are real, which makes the quantization more complicated because you would also need to implement this for the quantum theory. And with this, I stop, and I thank you for your attention.